2A, formerly 2B, but now 2A. Okay, we're in the right place. So we'll start with derandomization from algebraic hardness, treading the borders. This work is by Zeyu, Mrinal, Kumar, Ramprasad, Saptharishi, and Noam Solomon. And Ramprasad will give the talk.
Am I audible? Okay. So I realize now that Noam's affiliation is not Harvard University. He's now working in a startup which I don't know the name of. Okay, so I'll describe the various parts of the title as the talk goes along. So the talk is going to be about what are called algebraic circuits. These are standard models to study the complexity of polynomials based on basic operations required to compute them. So it's the standard setting where the leaves are labeled by variables and you have addition and multiplication gates. And sometimes you also add constants on the edges to just basically indicate that multiplications over the base field come for free. You're only going to charge for multiplying polynomials or adding polynomials together, and the output naturally computes some multivariate polynomial. And normally the size is just denoted to be the number of nodes in this circuit. Sometimes it's the number of wires, but it doesn't matter for the sake of this talk. And throughout this talk, I'll just be assuming that you're working over a field like the reals or the complex numbers or something, so that there's no finite field things that happen. Okay? And there are two main important questions when it comes to algebraic circuits. And the first one is a sort of lower bounds question, which is that we want to find a family of explicit polynomials that require large algebraic circuits. That's the lower bound question. And the second sort of question is the more algorithmic nature, where you're given a circuit and you want to say something non-trivial about the circuit. The simplest of which is you are provided a circuit and you want to check whether this circuit is computing the zero polynomial. And this is called the polynomial identity testing question. And we'll be focusing on a very specific form of this identity testing question, which is the notion of computing hitting sets. This is also called black box identity testing, where what you want to do is, given certain parameters of this small circuit, like for example, the size being S, the degree being D, the number of variables being whatever, and so on, you want to compute a small list of points such that every non-zero algebraic circuit with these parameters is guaranteed to evaluate to a non-zero value on one of the points in the set S, set H. Such a thing is called a hitting set. And in some sense, this is like an identity test where you're only allowed sort of evaluation access to the circuit. And turns out, even though one is a lower bound question and the other is an upper bound question, these two problems are very, very intimately connected to each other. Okay? So let's talk about what is called the polynomial identity lemma, or the Schwarz-Zippel lemma, or the De Mello-Lipton-Schwarz-Zippel lemma. I mean, turns out it was proved several times earlier, which basically says that if you have a non-zero polynomial of degree d, this degree could be either the total degree or the individual degree. It doesn't matter for this. And if you choose a set of your field of size at least d plus 1, that is one more than the degree, then if you just take the grid defined by this set S, your polynomial is guaranteed to be non-zero on one of these points in the grid. So in some sense, what it tells you that you have a hitting set for let me use this notation C n d star to basically mean n denotes the number of variables, d is the degree upper bound, and the third coordinate is supposed to be the size upper bound, but this is a lemma that basically says it doesn't care about the size of the circuit. If you promise to me that the degree is at most d and the number of variables is at most n, here is a hitting set of size d plus 1 to the n. Okay? And okay, we could ask, I mean, like, no, are there smaller hitting sets if I tell you that the size is bounded by a parameter s? And counting arguments tell you that yes, there are hitting sets of size about s squared. And the main question therefore is like, can we find one such explicit example? And we don't know at the moment. Okay? Okay, cool. So there's these two questions of finding explicit hard polynomial families versus finding explicit hitting sets. And turns out we can go between these two questions. So in particular, if you know that if somebody gave you a hard polynomial family, then Cabanets and Impagliazzo showed how you can use this to construct explicit hitting sets. And on the other side, Heinz and Schnorr and Agrawal showed that if you know there are explicit hitting sets, you can use this to construct hard polynomials. And we'll primarily be focusing on this other direction, which is like you're given a hard polynomial family, and you want to go to explicit hitting sets. That is, you want to get derandomization from algebraic hardness. Okay? So how are heating sets typically constructed? Almost all heating sets so far basically do what is called a variable reduction. That is, you have a non-zero circuit to begin with. You want to reduce the number of variables while retaining the fact that it was non-zero. And by doing a variable reduction, what I mean is in place of the variables x1 through xn, you are just plugging in g1 through gn, which are polynomials on fewer variables, and somehow which retains the non-zeroness of the circuit C. And this has a name. It's called the heating set generator, which is just a tuple of polynomials which has the guarantee that for every circuit in your class of interest, the circuit is non-zero if and only if the composed one is non-zero. Okay. And there's a bunch of parameters which are relevant. One is the degree of the generator, which tells you how complicated these GIs are, and the stretch is, or the shrinkage is like with respect to how much what is the number of variables you can reduce to, thing. Okay. So, and it's a very simple observation that once you construct a generator of low degree and pretty good stretch, then you automatically get an explicit heating set because it just follows from the polynomial identity lemma. You now have a non-zero polynomial of degree at most d times capital D because you plugged in, degree D guys, and so therefore you just use the polynomial identity lemma. The crucial thing is that instead of having an exponent of n, you now have an exponent of L, which is substantially better. Okay, great. So what do we know about, if we start off with a suitable hardness assumption, what sort of heating sets do we know? So Cabinets and Impagliazzo showed that the harder your polynomial family is, the resulting heating set that you get gets better and better. So in particular, if your polynomial family requires super polynomial size, then you can get a heating set which is sub-exponential. And on the other hand, if your polynomial family has size something like say 2 to the root n or 2 to the n to the epsilon for some epsilon, then your heating set will be quasi-polynomial. And if you assume the best lower bound you could hope for n-variate multilinear polynomials, you end up getting a heating set of size quasi-poly again. So recently we showed that there is a slightly weird regime which is usually it's a little esoteric here, here you have a family of polynomials on k variables, and I'm thinking of k as a constant, and the growing parameter is now d, and you want to ask, okay, what sort of size lower bounds can we prove here? If you can prove a d to the epsilon lower bound, then you can almost de-randomize PIT. So a natural question here is, what sort of hardness do we need to assume for us to say that this would mean that you have poly-sized heating sets? And in this talk, we show that if we have a similar lower bound guarantee like in the previous one, except there is this notion of size bar, which is also called border size, which I'll get to shortly. And if that happens, then we can show that you do indeed get poly-sized heating sets. Okay, so let me just state the result more precisely. Suppose we have a polynomial, a k-variate polynomial P of degree D. Then we can construct a generator, which is this explicit map, such that with the following guarantees, that this generator is reasonably explicit. It's like d to the order k. Think of k as a constant, so it's poly-explicit. And for every non-zero circuit, if it so happens that C when composed with this generator becomes 0, then the border size of P cannot be too large. So the contrapositive will say that if P was hard enough, then the resulting generator is actually going to be a heating set generator for your class of interest. So just to set some parameters, you would typically want to think of the degree of the polynomial you're using to be a much larger polynomial in the number of variables you're trying to fool. Okay, this is the main theorem that we'll prove, and I'll state. And so there's a bunch of nice corollaries. One is the thing that I stated in the previous slide, which is that if you have a family of polynomials on k variables where the growing parameter is the degree, and you have a border size lower bound of about d power 1 plus epsilon, then we can get a heating set for poly size for general algebraic circuits. Okay. Another consequence that you have is that there was a recent result which we had, which basically says that suppose you focus on this class of just k-variate polynomials that have degree at most s and size at most s. And suppose somebody told you that there is an explicit heating set of size s bar k minus epsilon for any epsilon greater than 0. Then we showed how you can sort of bootstrap this hitting set to get nearly polynomial sized hitting sets. And now we can do the same thing where you can get an actual polynomial sized hitting set, but except we now work in this border setting. So that's another consequence of this theorem. So what's all this border stuff that we are talking about? So I'll just spend 2 slides on this, not going into detail. Basically, the technicality is the following. So suppose you look at the space of all polynomials. There's this sort of blob of polynomials of small size that we care about. The problem is that the picture is not very sharp like this. The problem is, it's very fuzzy around the edges, which basically means that there are polynomials which are arbitrarily close to those polynomials of small size, but don't have small size themselves. So this shows up in, for example, tensor rank and so on. It shows up in a lot of, areas. And so this is what I mean by saying that when we say that something has low border size, I mean that it's not even close to polynomials of small size. That's what we mean by border size. There's only one trick about the border that we'll ever have to use. So I'll just state that. So suppose I give you a circuit of sizes that computes a polynomial, and we care about the highest degree homogeneous component. There's a standard trick that lets you extract the homogeneous component with a small blow-up. But in the border, you can do this without any blow-up. So suppose the polynomial is computing P0 plus P1 blah, blah, blah till PD. We just replace each xi by xi over epsilon. So naturally, each of the homogeneous parts will scale by epsilon to the d. And you now just multiply by epsilon to the d overall. And if you now let epsilon tend to 0, you basically extract out the homogeneous part. And you've paid for nothing in size. And this is really the only trick that we use in the paper. Okay, so let me give a brief sketch of how the proof works. And okay, so let me first describe what is the generator. So this is our hard polynomial. What we are going to do is we are going to basically just add up two sets of variables y and z and just think of the Taylor expansion. Just expand this polynomial out into a whole bunch of terms. And we'll just, so these are just the standard Taylor expansion around the point z. The generator is basically going to collect terms of the right degree and put them in each of the coordinates, and it just takes the first n coordinates. So in principle, so basically delta 0 corresponds to just the degree in y being 0 part, which is just p of z. Delta 1 is going to be, in some sense, the gradient, and so on. So these are the coordinates of the generator, and we basically show that this generator works. Okay, how do we go about showing that some generator like this works? The standard way the proof was is just say that let's assume, on the contrary, that there is a circuit C which is not fooled by this generator. And we'll basically show that we can use C to somehow reconstruct P from it. And that will contradict the hardness for P. And it's really, just in the second part where the structure of the generator works, because you're going to design the generator in such a way that the reconstruction process is easy. And the main idea is to just think of a circuit evaluated on the generator being 0 as a differential equation that P satisfies, and somehow try and extract out P from this. A similar strategy was also used by Koparthi in the list decoding algorithm for univariate multiplicity codes, and this is really a multivariate analog of the same thing. Okay. Okay. So just as just to get a sense of how things work, suppose we have the univariate setting where I have an equation of the form C of P, P prime, P double prime equals 0, where P is just a univariate polynomial, and I am given access to the circuit C. How do I find out all polynomials P that satisfy this? And the idea is that suppose P was something of this form, and suppose you knew the first 3 terms of P. Let's just imagine you just guess those first 3 terms. And the idea is that we'll just recover all the other coefficients of P one by one. And if you just look at this equation, it looks like A0 plus A1t plus a bunch of terms, blah, blah, blah. And the reason I'm writing it this way is because if I truncate everything beyond t squared, that is, I ignore terms of t squared and above, then you have an equation of this sort. And the key observation here is that A3 is the only thing I don't know at this moment. And this is a linear equation in A3. And so you can, in some sense, solve for this linear equation. This is what it will look like. You will require the denominator to not vanish, so it needs to be some non-degenerate stuff here. But basically, this is just the standard Newton iteration. And this is essentially what we do in our setting. So, we have an equation of this sort, and I assume that it is non-degenerate in whatever that means. So there's some technical reason why I'll need this. So now we'll just assume that P is made up of a bunch of homogeneous parts, and I'll assume that I can guess the first n parts. I'll just compute them by brute force. This requires size about n to the order k. And each of the other parts we'll just do by Newton iteration one at a time. We'll recover each of the other homogeneous parts one at a time. And there'll be a similar such step that we have. And the main technicality really comes from the fact that this is an iteration we'll have to run roughly d times. And it's important that every step of the iteration does not create a multiplicative blow up in the circuit size, because then we won't be able to do this for d steps. And because we are really trying to avoid all sorts of blow-ups, that's really where the border comes into play. And it helps us save on some multiplicative factors we would have obtained otherwise. So pictorially, this is roughly what it looks like. We'll assume that we have access to all homogeneous parts up to the point, compute a bunch of these deltas, plug in the fooling circuit C on top of all of them, and then do some interpolation type thing. So this will help us recover the derivative that we care about, except there will be this higher order junk that is involved, which we need to get rid of. And at this point, you do some border trick and get rid of all the higher order junk. And you don't pay much in the size at all. And effectively, this is going to be the new circuit, and you rinse and repeat. And all the parameters just works out, and you eventually get that in order to recover all d parts, you will roughly end up spending this much amount of time. Okay, so I have about a few minutes left. So this is roughly the end of the proof. And subsequently, there have been some recent improvements which seem cool. One is that, so we made all this fuss about the border and about how this border was crucial because we wanted to extract these homogeneous components and so on. Well, turned out we can actually get rid of the border assumption completely. So whatever we were using the border for, there is a slightly more careful homogenization that we can do. It becomes slightly weaker than what we have last time, but in terms of the final asymptotics, it doesn't make much of a difference. So, so this was subsequent to the submission of this paper. So now there's no fuss about the border. You can just assume the standard hardness assumption, and you get the same sort of lower bound. And there's this really unusual improvement to bootstrapping that came up as a consequence of this. I just want to recall the previous bootstrapping result. It says that let's assume that epsilon and k is some large but arbitrary constants. Now, I want to look at the class of k-variate polynomials of degree s and size s. And suppose somebody told us there is a hitting set of size s bar k minus epsilon. Then we showed that you can actually get polysize hitting set. This was one of the corollaries of the result that I mentioned. Now, it turns out we can improve this to the following form. Suppose you have a hitting set of size 1 smaller than the trivial hitting set. So the trivial hitting set has size s plus 1 to the k, and all I want is to say 1 point. If you can say 1 point, you actually get polysize hitting sets for general polynomials. I do want to stress that for all s greater than or equal to k is a crucial. It hides a lot there, which means you're really working in this regime where the number of variables is really small and the size is humongous in the number of variables. But all this is saying is that all you want to do is save 1 point from the trivial set. And if you can do this, you can actually solve all of PIT. Okay, so let me, this is what I was saying. So I don't know whether we should think of this optimistically, pessimistically, whatever. Okay, so let me just conclude. So basically we showed that with the right sort of hardness assumption, you can get complete derandomization of polynomial identity testing. And this also helps us bootstrap a ridiculous improvement on PIT by just saving 1 point, and that seems to be sufficient to just bootstrap to the general setting. So currently there are parts, because the proof in the generator is very derivative based and so on, there are reasons why we seem to require the field being characteristic 0. I believe there should be versions of this generator that should work for all characteristic fields, but at the moment we don't know how to do that. And secondly, it somehow feels like the hardness that we seem to need in order to fool a certain circuit class depends on the degree of the circuit and not just the size of the circuit. And for a while we thought that this should not be the case and that we should be able to get around this, but it's unclear if we can get around this particular part. Yeah, and that's all I wanted to talk about. And yeah.
Questions?
Yeah.
All right.
So I have this question about like saving one point from
Uh-huh.
being set. So why couldn't you just remove, I don't know, the L0 point and be done?
Sorry?
Like a non-zero polynomial, like why couldn't I just remove one point and have it being set?
No, so but I mean, no, but in the sense that the polynomial that does not vanish only on the all zeros point will also have some small size, right? So that would not quite. I mean, I'm a bit confused with what.
I guess I'm.
Okay. Huh. Yeah.
All right. Shall we thank the speaker again? Thank you.